500 million years after the Big Bang, the universe was supposed to be simple, small, faint, just getting started. Then, JWST looked deeper, and instead of baby galaxies, it found tiny blazing red objects already shining like fully built cities. Too bright, too compact, too early. If these are galaxies, they grew impossibly fast. If they're not, then something even stranger is lighting them up.
JWST found tiny, extremely red objects that are far too bright for how early they appear. That breaks our expectations for baby galaxies. What are they? Overgrown star factories that shouldn't exist yet, or supermassive black holes hiding in plain sight? Stay with me as we decode their infrared fingerprints and test both possibilities, step by step, to see which story the light actually supports, and what it means for the timeline of the first structures in the universe. If early galaxies should be faint and bluish, why are these points tiny, scarlet, and blazing like lighthouses from 500 million years after the Big Bang? By the standard playbook, the first systems should be simple. You pack a young galaxy with hot, short-lived stars, you get a lot of ultraviolet light. Slide that light through the expanding universe, and JWST's near-infrared filters should still catch a blue-leaning signal. Early on, there isn't much metal-rich dust to soak up the blue and glow red, so the expectation is straightforward, small, faint, and skewed to the blue end. That's the baseline many models predicted before the first deep fields rolled in. Then JWST stares deep, and the scene won't match the script. We see compact sources at redshifts around 7 to 13 with extreme infrared colors and surprising luminosity. Instead of pale, tentative seedlings, the data show scarlet pinpricks with serious output. The universe's nursery is supposed to hum. Instead, it's roaring. These dots look like fully booked cities when we expected small towns, with energy budgets that stress the early timeline. So what makes something look red in the near-infrared? 3 routes matter here. First, cosmological redshift stretches all wavelengths, moving blue and ultraviolet into JWST's redder bands. That's the default effect for anything distant. Second, the Balmer or 4,000 angstrom break, an imprint from the atmospheres of stars, can carve a sharp step in the spectrum. When that step falls between 2 filters, one band drops while the next shoots up, creating a red color even without dust. Third, dust reddening absorbs and scatters short wavelengths and lets longer wavelengths through, leaving a redder slope. Each route leaves a different fingerprint across NIRCam filters. A clean redshifted continuum gives a smooth trend. A Balmer/4000A break creates a cliff between adjacent bands. Dust builds a rising, curved slope with telltale flattening in the reddest channels. The photometry backs up that something intense is happening. Some dots show steep color changes over small wavelength steps, pointing to strong breaks. Others stack so much flux into the reddest bands that you either need an enormous population of older stars or extra emission beyond Starlight. In some cases, those red bands can be boosted by bright emission lines that fall right into the filters, making a small object look heavy and mature when it's actually lit up by lines. To turn colors into physical properties, astronomers use SED fitting, short for spectral energy distribution fitting. You feed the code the measured fluxes in each filter and a library of model spectra that span star ages, metallicities, star formation histories, dust levels, and sometimes non-stellar components. The code searches combinations that best reproduce the data and spits out likely ages, masses, and dust. Here's the catch: age, dust, and metallicity can mimic each other. A dusty young galaxy can look like an older, dust-free one with a strong Balmer break. Strong emission lines can masquerade as a massive red stellar population if the filter swallows the line. Even the assumed star formation history matters. A recent burst will skew colors differently than a steady build. JWST's resolution adds another clue. Many of these dots are tiny even for the telescope's sharp eyes. Effective radii fall to a few hundred parsecs or less. If the light is stellar, squeezing that luminosity into such a small footprint drives the surface brightness way up. You're talking intense star formation rates per unit area, the kind that push gas, radiation, and feedback to their limits. If the light isn't stellar, a compact engine starts to look more plausible. So the colors and the compactness set the stakes, but don't declare a winner. Either star factories matured at breakneck speed, packing huge output into tiny volumes, or something non-stellar is punching above its weight. To decide, we have to read the light more closely, line by line, where subtle ratios and widths reveal who's really powering the glow. The spectra whisper a culprit. Are we seeing starlight or the glow of matter falling into a black hole? Here's the split. One path says these are ultra-massive, ultra-young galaxies that somehow built huge stellar populations almost overnight. The other points to active galactic nuclei, where gas spirals onto a fast-growing black hole and floods the spectrum with non-stellar light. Both can look red and tiny. Both can be bright, but they leave different fingerprints once you look past the colors and into the lines and shapes of the spectrum. If these dots are dominated by stars, the case leans on features that signal maturity. A pronounced spectral break, like a Balmer or 4,000 angstrom step, hints at a population that isn't all newborns. That pushes the mass-to-light ratio up, so you need a lot of stars to produce the observed brightness. The implied stellar masses can climb toward 10 to 100 billion suns at redshifts where the universe is only a few hundred million years old. To get there, star formation must run at extreme rates and stay coherent in a tiny volume. The dynamical times, the time it takes gravity to rearrange gas and stars, are short in such compact systems, so the buildup has to be fast and efficient without blowing itself apart. Dust would help explain the redness, but dust itself needs metals from earlier stars, which adds another layer to the timeline. On the AGN side, the clues shift. Broad emission lines, when they appear, come from gas orbiting close to a black hole at thousands of kilometers per second. Even when lines aren't broad, very high equivalent widths can supercharge the broadband flux if lines like H-alpha or O3 land inside a filter, creating a red, bright appearance without a massive old stellar population. The continuum can look like a power law rather than the bumpy shape of starlight. And the morphologies stay compact at the core, consistent with a central engine that outshines its host. All of that fits neatly with the tiny effective radii and high surface brightness. So how do you tell? You go to the tests. JWST's NIR spec can measure line ratios that separate star formation from AGN activity and line widths that reveal whether gas is moving at stellar speeds or near a black hole. A mid-infrared excess can flag warm dust heated by an AGN torus. X-ray data are powerful too, but non-detections don't clear the AGN because gas and dust can bury the X-rays in a Compton-thick shroud. Variability is another probe. If the source brightens or dims over months, a compact engine is likely at work, while a whole galaxy of stars changes more slowly. We've seen both kinds of examples. Some little red dots show extraordinarily strong O3 plus H-beta that land inside NIRCam filters at these redshifts, inflating the red bands and mimicking a heavy, old galaxy. Others reveal AGN-like traits. Broad H-alpha at rest frame optical, high ionization lines like NV or CIV in the rest frame ultraviolet, and blue power law slopes beneath the redness once you isolate the lines. In those cases, what looked like an impossible mass becomes a more modest galaxy lit up by its nucleus. That still leaves the growth problem. If many dots host AGN, the black holes had to reach millions to billions of solar masses very fast. Two seed tracks compete. Light seeds from the remnants of the first massive stars, and heavy seeds from direct collapse of pristine gas clouds. Light seeds need near-continuous, near-Eddington feeding to hit the targets on time. Heavy seeds start bigger, easing the pace, but they require rare conditions and rapid inflow to form at all. As more spectra come in, the balance is shifting. A growing fraction of little red dots show AGN-like signatures or line-boosted photometry, moving many from impossible galaxies to hidden black holes, while a subset still reads as compact, dusty starbursts. If black holes lit the early universe this brightly, our cosmic timeline needs edits, starting with how fast the first structures formed. So here's the working answer. The little red dots aren't one thing. You're seeing a split population, compact, dusty star factories pushing intense surface brightness, and a large share of early, rapidly feeding black holes powering AGN-like light that outruns our timeline. Now the test shifts to time and detail. Watch the next Spectra and monitoring campaigns. If more show AGN fingerprints, diagnostic line ratios, broad components, mid-IR warmth, short timescale variability, we'll rewrite the opening era of galaxy growth. New JWST cycles are locked on these targets. The data will tell us whether we found the universe's first cities or its first monsters.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.